I basically gave my talk a little bit of an homage to Dr. Strangelove about how I learned to stop worrying and love ICP-MS. Before I begin, I'd like to acknowledge that the land upon which I live and work is the traditional unceded territory of the Algonquin and Anishinaabe people. So when I was asked if I could present something on the use of ICP in radionuclide metrology at NRC, I said, nope, we don't use it. But then the follow-up was, didn't you do something with protactinium isotopes? I said, yes, but we didn't use ICP. And so I was told, okay, talk about that. And I was, this slide kind of sort of indicating that while, a lot of us in radionuclide metrology don't have ICP capability, also people with ICP can benefit from decay counting techniques. And this was maybe not so mysterious after all, because as you could see by Ellen's talk and Dante's, you can take a lot of advantage from having both capabilities. But before I can tell you that story, I have to tell you this story. It actually isn't true that that in my lab we have not used ICP-MS, and so there have been a few cases. One in which we quantified a nickel-60 spike for the sample of production of a synthetic cobalt-60 radiochronometer CRM. We've also used the ICP, and when I say we've used ICP, basically I take advantage of the capability that my colleagues Zoltan and his group have, and so we also used it to identify and quantify non-radioactive impurities in the manganese sulfate bath solution, which is used for primary method of neutron emission rate. And then finally, myself and my colleague in radionuclide metrology, we actually went up to Laval University and had some training in order to implement a cloud point extraction method, so a chemical method for rapid uranium radiochronometry measurements. And so that also included the use of ICP and training on an ICP multi-collector. And then finally, while it's not radionuclide metrology, my colleague Zoltan Mester and his group there prepared 3 UOC uranium ore concentrate CRMs, which I won't defend, but I'll just state is the most characterized CRM ever prepared. So the story I wanted to tell is how a physicist was invited to do some chemistry training, in particular for uranium radiochronometry. So there was an offer by LBNL in the US to train some Canadian government scientists, and there were all the spots, but one was taken up by chemists at other government agencies. And in order not to waste this opportunity, they needed one more individual, and I was asked if I'd be interested in going. And so I did, as the only physicist in the group. And it was done at Ross Williams' group at LBNL, is a fantastic location. And we covered the techniques of uranium radiochronometry, the use of TIMS and ICP-MS, and we talked about the radiochemistry of uranium-thorium separation. Now, in uranium radiochronometry, there are multiple radiochronometric pairs. And so while we were studying just the thorium-uranium, thorium-230, uranium-234 pair, there's also the protactinium-231, U-235 pair. And essentially the agreement or disagreement between these two radiochronometers in any given sample will actually give you further nuclear forensics information, for example, in terms of potential chemical preparation of the sample that might lead to its origin. But as the presentations were given to us, almost as an aside, there was this expression of frustration in the difficulties in measuring the protactinium-231 in ICP, as another isotope of protactinium, namely 233, protactinium-233, was needed to evaluate, the efficiency of collection and correction, determination of correction factors in the mass spec measurement. And so what was described was with no such atom counting standard, they used an ancient standard of soil. I think it was the white shell standard, where the protactinium-231 in this sample is deemed to be or assumed to be in secular equilibrium. So that was used to standardize a protactinium-233 sample that was incidentally derived from milking a neptunium-237 generator. And that then certified protactinium-233 standard was then back used to standardize the protactinium-231 standard. So it was a bit of a roller coaster ride there. And what I pointed out at this presentation was, well, protactinium-233 is right in our sweet spot for radionuclide metrology. It's got a shortish half-life. It's a beta emitter with a perfect coincidence to gamma emission. I thought this is fantastic. So I thought, well, why don't you just get something from an NMI or NIST, to calibrate an ion chamber, and then simply convert it to your atom counting standard, and then you're good to go. And so it was through that discussion that we led to, well, it was on the books, but led to a comparison of 233 as well as 231 in the preparation of a 231 atom counting standard. And so what you can see here is the comparison of the 233 with the comparison with the atom counting standards from LBNL, as well as the radiometric measurements from primary methods and metrologies, NMIs, NIST, and NRC, and I believe NPL is also there as well. Just as an aside, NRC also did a side project to look at an alternative production method for protactinium-233, which didn't depend on having a very large legacy neptunium-237 source in order to milk. The other thing I'll sort of say here is that you can see this is the comparison of the 231 standard. Again, this is it's radioactive. It's pretty much stable, but it's radioactive nonetheless. And so this is also something that can be measured. And this is an example of what was really remarkable about the previous talk that Len showed, is when you're doing this purification or preparation of a sample, it's important to keep both the radiometric side and the mass spec side in mind, as the purification of the 231 was not perfect, and so there was still some residual actinium-227, resulting in a necessary and the requirement to correct the radiometric measurements. And because this was unknown at the time, it was difficult to determine that, and so there was a large uncertainty associated with that. But in particular, this alpha spec measurement that NIST did, where they also used a protactinium-233 spike here, was excellent. And I wish I had thought of that and tried that as well. So that's about it. It's a very short story, but I will conclude by saying that we're most likely will be adding this into our suite of capabilities in the next few years. Looking forward to doing various things like half-life determinations, non-radioactive impurity detection, comparison of radiochronometry methods for nuclear forensics analysis. What can be done in 1 week, 1 month, 1 year, etc. Potentially measuring radioactive xenon isotopes and more. And that's what I'm looking forward to sort of learning from in the next few days. And I would indicate that for us at radionuclide metrology, it has never been an issue of adding the capability that was in question. It was more, human resources aspect in order to maintain and utilize this device should we get it. And that's about it. Thank you.